Hello everyone, my name is Amir Hossein and I'm going to talk about our paper on analytical derivation and comparison of alarm similarity measures. This is a joint work from our team in the EC department of the Isfahan University of Technology. Industries reportedly lose billions of dollars annually due to plant problems. Many can recall these catastrophic industrial incidents that bring the safety of the people and the environment into danger. By monitoring and placing reliable alarm systems, most of these disasters could be prevented. Most of the time, outcome of a monitoring system is an alarm. The alarm is a single variable with a range of 0 and 1 that indicates the process variable is in a normal operation or exceeds its limit. For example, for this process variable, two high and low alarms are set. When the process variable exceeds these limits, the alarm will be turned on and gets the value 1. An industrial process includes many devices variables that are interconnected. These interconnections imply some level of correlation between process variables. Since the alarms are defined on process variables, then the alarms will be also correlated. So if we have a poor design of alarms, this might be a nuisance to operators. For example, if one fault triggers, then a large number of alarms will be turned on. By knowing how correlation between process variables affect alarm correlations, we can make a better design of alarm system. In the following, we will talk about the different type of alarms and see how the distribution of process variables and the choice of alarm limits will affect the correlation between alarms. Alarms are often triggered if a process variable exceeds its predefined limits. For each process variable, many different alarms can be defined. We can define a set of high, high, low, and low alarms for most of the process variables. When a process variable is higher than a certain limit, a high alarm is activated. If it continues to rise and passes another higher limit, a high alarm is triggered. For example, what we have for 7th and 8th sampling instances. Similarly, when a process variable is lower than a certain limit, a low alarm is activated. If it continues to fall and passes another lower limit, a low alarm is triggered. We can collect the information of all alarm tags related to one process variable into one alarm sequence. We call it multi-valued sequence of alarm. In multi-valued sequence of alarm, each individual of high, low, and low alarm tags are multiplied by 2, 1, -1, and -2 respectively. Notice that it is assumed that at each sampling instant, only one of the alarms can be activated. To calculate the similarity measures of two alarm sequences, we assume that underlying process variables follow a Gaussian distribution. Gaussian distribution is assumed for brevity. The process variable can follow any distribution. In this case, f and f2d are be defined accordingly. Consider this setup. Let xi and xj be two correlated process variables with Gaussian distribution and the Pearson correlation coefficient rho. This means that every sample of xi is correlated with its concurrent sample of xj with coefficient rho, and it's independent from other samples. Assume that there are some limits configured for xi and xj, so we can have two corresponding alarm sequences. The question we would like to answer is that how the correlation between xi and xj affects alarm sequences correlation. We split this question into three different questions. First and second, what is the Pearson correlation coefficient of two corresponding binary alarm sequences and multivalued alarm sequences? Third, what is the Jacquard similarity index of two corresponding binary alarm sequences? In the following, we will answer these questions. For two random variables x and y, Pearson correlation coefficient is calculated with this formula. where mu and sigma are the mean and the standard deviations of a variable respectively. Assume that there are two high alarm limits configured for xi and xj with thresholds set at hi and hj. Let bi and bj be the two corresponding binary alarm sequences. In this paper, we prove that the Pearson correlation coefficient of bi and bj can be calculated as this. As we can see, both of predefined limits, characterization of process variables, and correlation coefficient appear in this equation. So we can find the Pearson correlation of two binary alarm sequences analytically without having those sequences actually. Now assume that alarms, namely high high, high, low, and low low are configured for the xi and xj. With this alarm configuration, two multivalued alarm sequences, MI and MJ, are obtained. It can be easily verified that MI is a combination of binary alarms, where, for instance, BHI is the corresponding binary sequence for the high alarm. If we want to compute the expectation value of MI MJ, it will be a sigma over the expectation of binary alarm sequences. Each of the multi-valued sequences is a combination of 4 binary sequences. As a result, 16 terms will be created. So we can write an extension of the last equation to compute the correlation of multi-valued alarm sequences. In this paper, we prove that the Pearson correlation coefficient of MI and MJ can be calculated as this. Details of this equation are explained in the paper. High alarm and low alarm have the most effect in the correlation between alarms because they have a coefficient of 2 and -2, while for the high and low alarm it's 1 and -1. There are many different indices to measure the similarity between two binary sequences. One issue that needs to be decided beforehand is whether zeros are as important as ones in similarity. Some methods suggest that they have both should be given same importance, but the others only emphasize on ones. In the context of alarm data, a zero in the binary sequence means no alarm, which doesn't provide the operator with any new information. So for alarm data, indices that are only based on matching ones are preferred. An index in this category is the Jacquard index. For two sets A and B, the Jacquard similarity index is calculated as this equation, and for binary sequences Si and Sij, it's equivalent with this equation. Here, Aij is the total number of times where both Si and Sj are 1. Bij is the number of times where Si is 1 and Sj is 0, and Cij is the number of times where Si is 0 and Sj is 1. Hence, Bij plus Cij represents the total number of mismatches. Let Bi and Bj be the same setup as before. In this paper, we prove that the analytical value of the Jacquard similarity index can be calculated as this. Until now, different measures of similarity between two alarm sequences were discussed. In the following, we want to compare different types of similarity measures for different types of alarm data. To aim this, a Monte Carlo simulation is carried out. Also, we use the correlation color map to show and compare the results. For the case study, 15 different correlated process variables with Gaussian distribution but with different parameters are generated. We show the correlation color map of the original process variables at the left. These are the values we initially selected, and for the simulation part at the right, we generate the process variables according to this. High alarm limits are considered for all process variables with different thresholds, and their corresponding binary alarm sequences are obtained. The Pearson correlation coefficient for the binary alarm sequences is calculated. It can be observed that for binary sequences, both the analytical and simulation-based correlation color maps are identical. As we expected, the similarity of two alarm variables, more or less, are proportional to the correlation of the two corresponding process variables. Also, for each of the process variables, four alarm limits with high-high, high, low, and low-low are considered, and the corresponding multivalued alarm sequence is acquired. For the multivalued alarm, the Pearson correlation coefficient of these sequences is calculated. It can be observed that for multivalued sequences, both the analytical and simulation-based correlation color maps are identical. Also, as we expected, the correlation color map obtained from multivalued alarm sequences is more similar than the binary ones to process variables. The mere fact that different alarm levels are treated differently in this sequence significantly improves the correlation. And for the last calculation, the Jacquard similarity index for the binary alarm sequences is calculated. As we can see, the index is between 0 and 1, and it cannot measure the correlation between alarms that are obtained from the correlated process variables with coefficient less than 0. But for the positive coefficients, it's like a Pearson coefficient between binary alarms. The Pearson correlation coefficient and the Jacquard similarity are two widely adopted techniques in the context of alarm similarity. For each case, the similarity measure is analytically calculated and verified through Monte Carlo simulation. Also, we confirm these intuitive results. First, if two variables are correlated, so their alarms will be correlated too. Second, multivalued sequences carries more information and is expected to yield a better correlation. The source code of our implementation is available at this link at GitHub. Thank you for attending our presentation.